Welcome to ePathshala, postgraduate program for Masters in Architecture. Today in this module, we will be looking at a basic calculation of embodied energy. In this presentation, why we are doing it? Because it's relevant for architects. Reason is, you need to understand how the values of each embodied energy can be done. Now, for example, we are doing a house, but a lot of us are unaware of how much of embodied energy goes into a house. So this module is basically prepared in a way that how this will help architects to make decisions quickly and understanding how much of embodied energy goes into their buildings. So the question most of us ask, why do we need to calculate it? Unless until we calculate, how will you quantify it? The most important question that architects ask is, why to calculate embodied energy? Why is it so important? The reason is being that how do you or else justify that this building is either eco house or sustainable buildings, unless until you know what has gone into making this building and amount of energy that has gone into making this building predominantly more than anything else. So it becomes more important on designers to understand how to calculate it. Second, it makes the designers take decisions in selecting materials, because once you do a basic calculations of certain house, for example for a house that you have specified this materials are going into the house, then after doing it, then you can change, saying that no, it's quite a huge impact this building is doing, why don't we change this material from here? So, and the most important thing is, it gives you a step by step understanding as to how you can design a very low embodied energy building. Now in this module, we will go step by step to understand how this can be done. I will be going a little slow so that you can catch up with what exactly is going on and how the calculation goes through it. Firstly, there are two methods, as we saw in the previous module, that embodied energy are either in megajoules per kg or kilowatt hour per kg. Now these two methods are right, but to start using these methods, we need to get the values either in megajoules per kg or kilowatt hour per kg. Now we will do both the exercises. And the reason why we will do both the exercises is just to understand, okay, where does megajoules kg sit in comparison to kilowatt hour. It will almost be the same, but few here and there values, because megajoules per kg doesn't consider the total impact of the kilogram. So let's see how it goes about. Now to carry out for example, what we have done is, we have taken a building, a simple house which is situated in suburbs of Bangalore. Now the plot area is around 9.15 meter by 14, which is equivalent to around 30 feet by 45 feet. The total built up area of the house is around 78 square meter, which is equivalent to around 800 square feet. The height of the building from the FFL to the bottom of the roof slab is around 3 meter, and we have, for simple calculation, we have to consider that is a load bearing wall construction, no column construction. Now this is a floor plate. On the right side you can see the floor plate of the entire house. Simple house, 3-bedroom house, a living space, a kitchen, a attached bathroom, a utility at the back, and a common bathroom between the 2 bedrooms, and a small entrance porch for the vehicles and everything. Now what are the materials used? This is where it becomes important that we understand what materials have been gone into this building of this building. Firstly, the walls of brick construction. That's basically the common practice what we use. That's 230 mm for the external and 150 mm for the internal. Since being a load bearing structure, the central main wall in the center also has been used as 230. Next, 12 mm plaster, which is a standard, have been used all for internal walls as well as for external. We have windows in the house which have a wooden windows, which are around 400 by 75, which is 4 inch by 3 inch windows, with a 5 mm glazing used for shutters. All the doors are of the same thickness as the windows, that is 100 by 75, with a 40 mm thick window shutters, wooden shutters. The roof is normally 6 inches, which is 150 mm thick RCC roof, following the profile of the building. So we don't have anything additional, it just follows the profile of the plan. The flooring material used is a ceramic tiles. Cheap, simple, standard way of designing. Now this is a section which tells you what, there's a parapet, again the parapet, there's window and everything. So it's basically the same thing which what we just spoke about is explained in section. It gives you a height so that in section tells you calculation for calculation as well as for doing the calculation. Now typical section, this is basically a typical section. Now openings, so we have provided a window schedule, so there are different openings. So if you go back to the previous slide, you can see that the window W1, W2, W3 has been mentioned on the floor plate. So in this slide you can see the names, the length, the height, and what is the sill height, so that you exactly know where this window is being placed. First and foremost important step before we start calculating the energy is to calculate the areas for each one. Now how do you go about doing this? There's a simple method. The first simple method is just take the components. Let's not go into room by room, because at the end of the day the materials what we use or in the embodied energy are the components. So rather than going living area, dining area for each room and calculating, making it more complicated, what we have done over here is we made it simple. First start with 230 wall area. So wherever 230 wall is being used, calculate the total area. For this house it comes up to 158.8, which is around 160 square meter. Similarly calculate the 115 wall area, which is around 34. So you start doing it for each and every component. So there are around 8 components over here. So that's 230 wall, 115 wall, floor area, because floor would be different compared to the roof because you have ceramic tile, and the roof here may have asphalt or whatever you want to do, or you can even tile it on the roof. Then the window glass is something different because you have glazing over there. The timber door, because you're just doing the door. Then window and timber frames, because they are different frames. Timber door is just 40 mm as we mentioned before. So RCC beam and lintel has been put together as one single package because they are pretty much the same. Step 2, each component would have either one or more materials. Now for example 230 brick wall would not be just brick, it also has plaster in it, it also has painting in it. So it is like one component could have several into it. So what we do is step 2, we have classified each and every component into different materials of it, because at the end of the day you don't get the entire component values for calculating the embodied energy. Here you would require to break it down into smaller materials. For example brick. Now brick, we assume that leaving the gaps of filling the things, we have basically said it is 150 as same as the wall area. Small things would not matter much, so we have taken into the consideration. Cement plaster, so we are doing in as well as out, so you need to plaster in and out, so the cement would be the same. So whatever cement plastering doing, you need to paint it, so painting and the cement plaster remain the same. Similarly for 115, that is 4-inch wall, 4.5-inch wall, so that also is the same. So brick pretty much the same, the cement will be double. Flooring area, pretty much whatever the floor area is, you will do the same concreting, and then the cement ceramic tiles. Roof you will do the same, except that you will remove the parapets on the wall, and that's the reason the asphalt is less. Glazing, whatever the window size glazing are. Now coming down to window door frame, because since we are using only wooden, so we will keep it wooden, simple. 70 mm has been calculated. So here we have, first step was to look at the entire component, then the next step was to break up the component into smaller parts, which makes it easier to do the calculation. Step 3, now once you know how much of each component material has gone into each component, now it becomes that you need to go, there are different sources available online or books where they give you the value of the PER. Now in the previous thing we realized the PER is just the manufacturing value of a material, it's not the gross or the complete picture of that material from the site to the from the upstream to the downstream, which is the site. In this process we will just take the PER values. Let's not complicate the entire calculations. The purpose of this module is just to make ourselves aware as to how much the overall embodied energy of the building is and how we can reduce it. So in this step we are just looking at first. So what we look at, we need to, before do anything, because everything is in kg, and as you saw the values or methodology is megajoules per kg or kilowatt hour per kg. Now what values we have got is all in square meter. Now converting square meter into kg is a task that needs to be done. So that how is it done? Kg is nothing but the mass, so anything into volume into density would give you the mass. In this slide it will give you a clear understanding how this calculation goes about. Now first, for example, the brick you know that is 158.8 square meter. Now the volume is basically what, 0.23, because it's 230 thick, so you multiply into 0.23 and you will get the value as 36.5, and that the density of the brick is around 1920 as per the standards, and that multiplied will give you the mass. So similarly, for each material you need to convert the square meter into mass or kg. So this is very important, because without doing this it becomes very difficult to understand how the calculation would move forward. I hope this is much clearer. The next step after 3 steps is step 4. Now, since we know that there are 2 methods of calculating embodied energy, once you know the mass, let us start with the calculation of energy using megajoules per kg method. The following 2 tables gives you the embodied energy values of the material. First one, we know what the density is, we know what materials we are using it, but we need to know what in relation to what the PR value is of this each material. So what we use, this is the table which has been provided to you for simplification. That since we are using brick, and in brick you can see that is 2.5 in megajoules per kg, or megajoules per meter cube, it is around 5170. Now the difference between megajoules per kg or megajoules per meter cube is, megajoules per kg is basically based on your density. So that is basically getting your volume into density, volume, and then calculating the mass. But in megajoules per meter cube is basically directly calculating based on your volume rather than your mass. So these are the 2 methods that goes into it. So first one, so brick, you know, 2.5, so we are using brick. We are using concrete, so 1.3 over there. So you can go about looking at different. So we are using glass is 15.9, steel 13.2, paint 93.93. so you have most of the values which you require. One interesting value in this you can see is aluminium. Aluminium, the initial embodied energy for calculation of aluminium is around 227 megajoules per kg, but when you use a recycled aluminium, it becomes 8.10. You can see what happens, what is the impact of using a recycled material compared to a virgin material which is not being recycled at all. So this is basically the table gives you. Once you get this information from these tables, what you need to do is, against each material you copy that. For example, brick, you know the mass. So now the method what you are using to calculate is mass per megajoules per kg. So in the brick mass is around 70,000 odd into 2.5 will give you the total embodied energy of that brick in 231. Similarly, you do for the cement plaster. What you do for the cement plaster, you do the same. You know what is the mass of it, you know 6.1 is the embodied energy, multiply 6.1 into the mass, you get the total embodied energy. So you start doing it for each and every component of it. So once you do it for each and every, now one thing which I want to clearly mention over here is steel. Steel, what we have done over here is we have just taken 2% of the steel. Since it's very difficult to understand how much of steel thing is, normally as a standard method for a concrete slab 2% is used. So it means that the total area, only 2% of the area is steel. So that's how it's been demarcated. So once you get that, you get a total embodied energy within the building, which is that's almost like 5,08,290, which is quite a huge amount of megajoules that is being getting used. Now this value, if you just look at overall, it doesn't make any sense. So how do you compare with it? What do you need to do? In the further slides, we'll tell you what to do. Before that, we'll do one more step, which is step 5, which we calculate using megajoules per metric cube. As you know that there was a table which we had before, which had megajoules per kg values written for each material and megajoules per meter cube. The reason why we are doing this is just to understand the different methods of how you can compare, so that you are not caught when somebody is given you megajoules per meter cube and you don't know how to calculate it in the table, or somebody is given you megajoules per kg and you don't know how to calculate it. So in this case, what we will do is, in megajoules per kg calculation we use the mass. In this we will not use mass, we will use just the volume. So what we go about is same pretty much. Instead of the third column which we use mass over there, it's been replaced by volume. Embodied energy over here values are all in megajoules per meter cube, but in the previous calculation it was megajoules per kg. Total embodied energy is calculated, and it is pretty much the same as we got, few here and there because of the way it goes about, because there we have calculated density and maybe the density varies a little bit here and there, but pretty much on the same ballpark. In comparison, the total embodied energy of the house is calculated around 5 lakh. a typical house with a size like Bangalore would consume around 400 kilowatt per month. Therefore, for 12 months, the total operating energy is around 4,800 kilowatt hour. For the calculation purpose, let's say 4,000 of energy is converted into megajoules. So when you convert, because since the value of the embodied energy is megajoules, we need to convert the kilowatt into megajoules. And as I said, it's very simple. As we put in brackets, that 1 kilowatt hour is equal to 3.6 megajoules. So you multiply 4,800 kilowatt hour into 3.6, you get the megajoules per hour. The energy embodied of the house is equivalent to 30 years of operation energy. You would equate it that it will require around 30 years for you to achieve that embodied energy for a house, which means that if you by mistake, if you break the building or demolition the building before 30 years, then you have not even achieved what you have put, the amount of energy that has gone into your house. So it is important that in the previous modules which we have of embodied energy, has been clearly stated that it is important that the life of the building is longer. The reason is because of this. It makes the building viable, or else it is not viable because you have put so much of energy in operation and in embodied energy. By the time it meets the bracket of being more what you call gets the benchmark where both start meeting at the same point, if that doesn't happen, it makes it not practically logical to design such buildings. Summary: the entire, for whatever we have done in this module, basically, as initially when before the start of the module which I mentioned it, that this module is basically to give architects and designers an understanding of how to do a quick calculations. The purpose of this module only to demonstrate that how anybody sitting in an office can do a quick calculation, nothing more than that, and can come up with answers and solutions where either they can reduce it, get a better understanding, and how they can have a least impact onto the environment. So in summary, the calculations above are in PER value, as I have been mentioning in the entire module, that these are not based on the gross values, because gross values, if you want to do it, you would need to do a life cycle analysis, which means that you need to understand from where each one is going through. The data available on embodied engineering materials are imprecise. This is absolutely right. What I have given you the data could also vary from where you pick up the data. The credibility of the data needs to be verified. So be sure that either is one of the research institutes, one of the research institutions in the world that have published this data, because data can vary from places to places and from the where the resource comes from. So be very careful when you pick up the data for embodied energy. If megajoules per kg is the method followed to calculate the embodied energy, then all the embodied energy data available needs to be in it, or convert to megajoules per kg. You cannot mix megajoules per kg and megajoules per meter cube in the same calculation, because that will take your result in a different direction. So that's how it needs to be. The overall embodied energy between the two methods could vary, and therefore it is advisable that method adapted is clearly defined. So whenever you are doing your exercises and everything, please mention which method have you adopted to do the calculations. The above calculation do not take into account the transport. As I mentioned, that is just the PER value. It doesn't take into account the transportation of the embodied energy, as this would vary significantly, as well as destination and manufacturing. Above calculations are only for the energy of the material taken from the manufacturer. That's the PER value. While calculating the carbon emission, it would be important that the source of energy is known. See, here we are not doing the carbon emission. It could the next step, if you want to go into more detail, the next step would be to do the calculation for carbon emissions. But the module has been specified just to calculate the embodied energy. If you want to do the carbon emission, it needs to be important that you need to know the source. For example, whether the manufacturing plant is using coal generated power, hydro generated power, wind generated, or sun. That makes a huge impact on the way you calculate the energy. Embodied energy is a major investment of energy during your initial years of building until the operation energy exceeds it. Based on what we have learned today, what we have gone through, hope that this gives you a little bit of understanding as to how this calculation can happen. To make it more interesting and make it more easy for you to understand, what we have suggested is you calculate at least two material specifications or improvement where the embodied energy would be less than the reference case above. What I mean over here is, we have given you a base case reference, that this is what the total embodied energy of the building would be. Now we would like you as students to take up a small assignment where you would try to reduce this base reference to lower value. Now what it means is, you can basically take some other material with a lower embodied energy, mix match and see how this has an impact on the overall embodied energy of the same building. You can take the same plans and sections which we have given you, the area is the same thing as the part of your assignment. Hope this module was useful in terms of understanding how to calculate embodied energy. Thank you.